So the first type is Newtonian materials. As I have told you, Newtonian materials are those which follow Newton's law. That is, the equation used for such materials is neta is equals to S over G, or stress over strain. Now, the rheogram for such materials is straight linear line. This means with increase in stress, there is linear increase in the strain value. Very important point, the rheogram starts from the point of origin. This means that on application of a small amount of stress, there is rotation in the material. The slope of this equation is called as viscosity, and inverse of this, I have already told you, is known as fluidity. In some books, the slope is termed as fluidity. I again mention at that time, the both axes will be interchanged. So if G here, S here, this will be 1 by neta or fluidity. Fine. But in this case, the slope is called as viscosity. Now we come to viscogram. When we see the viscogram, on application of stress, there is no change in viscosity. The constant plateau phase or line is there. This is because Newtonian materials have property that their viscosity remains constant even on application of force. The example of such materials is water, dilute suspensions, dilute emulsions, syrups, glycerin, etc. You take example of a water, you apply force with the hand, with the drum, with the stick, whatever, its viscosity remains unchanged. And this is the characteristic of Newtonian materials. Apart from this, now we will discuss non-Newtonian material. First to discuss in non-Newtonian material is plastic. Plastic belongs to time-independent systems. Time-independent systems are of three types: plastic, pseudoplastic, and dilatant materials. So plastic is time-independent. Now the graph does not start, this is the rheogram for plastic materials. You will see the graph does not start from the origin. Rather, it starts from somewhere above the stress value. Then it behaves like a Newtonian material. So plastic materials, also called as Bingham's plastic, are those material which resist the initial stress, and once stress value is greater than the yields value denoted by F, they behave like a Newtonian material. Fine. Now again I repeat, plastic materials are those which resist initial stress. This means they do not move on application of a small stress. Movement is not there, they do not rotate. But as soon as the stress is greater than the yields value, the movement begins and they behave like a Newtonian material. In some cases, they may also behave like a pseudoplastic material, and thus these plastic materials are called as viscoplastic. So initially same, later they behave like a pseudoplastic material and called as viscoplastic. But otherwise, in most of the cases, they behave like a Newtonian material. Now, why this behavior is there? Again, before discussing the examples and behavior, let us come to viscogram. The viscogram for such material, there is slight dip in viscosity, then the viscosity becomes constant. Fine. This slight dip is because of excessive force which we are using in order to initiate the motion. Then they becomes constant or Newtonian like. Then the formula is similar to Newton's law, but there is S minus F component. This F is yields value. So this will follow linear relation only when S is greater than the F. The viscosity in this case is called as plastic viscosity, usually indicated by symbol U. And inverse of plastic viscosity is termed as mobility. Fine. Let us now discuss examples. The examples of plastic materials are concentrated flocculated suspensions. Now, these concentrated flocculated suspensions, initially their particles are in closed flocculation state. So initially force is required to break this particle. Till these particles break, there is no movement. So when force is greater than the force of flocculation, here force of flocculation is yields value, particles get separated and fluid begins to flow. This means when you apply force, they remains unchanged, there is no motion. Slowly force increases and becomes greater than the force of flocculation. These concentrated flocculated suspensions now become separated, particles are away from each other, they become more fluid and they tends to move with the stress. Such kind of behavior is called as plasticity, and this most probably is shown by concentrated flocculated suspensions.